Hello everyone, this is Fauzia. In this video, I'm going to show you step by step how to answer paper 2, October 2020, variant 2-1. 1A1, define the moment of a force above a point. Moment definition, force times perpendicular distance from pivot. Okay, next, determine the SI base unit of the moment of force. So by definition, moment is force times perpendicular distance. SI base unit for force is kg ms negative 2 and unit for distance is meter. So become kg m squared s negative 2. One B, a uniform rigid rod of length 2.4 meter is shown in figure 1.1. This is length. The rod has a weight of 5.2 Newton, and is made of wood of density 790 kg per meter cube. Density 790 kg per meter cube. Calculate the cross-sectional area in millimeter squared of the rod. Okay, so if you want to calculate area from the volume equal to area times height. So height is 2.4. So what is your area? So first of all, we have to calculate volume. So how to calculate volume? So we use formula density mass per unit volume. Density given, we want to calculate volume, and another one mass. How to calculate mass? From the weight. So weight equal to mg 5.2 mass 9.81. So mass around 0.53 kilogram. Then you substitute mass here 790 mass 0.53 per volume. So volume equal to 6.7089 10 power negative 4 meter cube. Okay, then substitute 6.089 10 power negative 4 area. Height is 2.4. Then area is 2.79 10 power negative 4 meter squared. Okay, now how to change from meter squared to millimeter squared? So now become, so area 2.79 10 power negative 4 meter squared times 10 power of 6 millimeter squared. So final answer 2.79 10 power of 2. 2.79 10 power of 2 millimeter squared. 1C, a fishing rod AB made from the rod in B as shown in figure 1.2. So this is the rod. The tension T in the string is in the direction perpendicular to the rod. The rod is in equilibrium and inclined at an angle 56 to the vertical. The forces and the distance along the rod of points A, B, C, and D are shown in figure 1.2. C1, show that the compartment of the weight that is perpendicular to the rod is 4.3 Newton. Okay, so we have to show. We might make it this weight perpendicular, look like this. Okay, right. So this is weight. Show that. So weight equal to W. Here, sine theta. So weight is 5.2 sine 56 degree. So we have 4.3 Newton. C2, by taking moments about an A of the rod, calculate the tension T. Okay, so this is the figure. This is the pivot. So this is my turning point. Now we have to determine the clockwise and anti-clockwise moment. T here oppose the motion or opposite direction from my turning point here become anti-clockwise. Stick same direction become clockwise, and then weight opposite direction become anti-clockwise. Okay. So now we have from the principle of moment, clockwise moment must be equal with the anti-clockwise moment. Okay, so what is the clockwise? Clockwise is stick. So stick 4.6 perpendicular distance to the pivot here. Perpendicular distance 0.6 plus 1.2 become 1.8. 1.8 equal to anti-clockwise is weight perpendicular distance here. Okay, this is weight perpendicular distance sine 56 times 1.2 and T perpendicular distance the whole thing 0.6 plus 0.6 plus 1.2. So total 2.4. So calculate T equal to 1.29 Newton. 1.29 Newton.
Number 2, a small block is lifted vertically upward by a toy aircraft as figured in 2.1. As a block is moving upward, the string breaks at a time t equal to 0. The block initially continues moving upward and then falls and hits the ground at t equal to 0.9 seconds. The variation with time t of the velocity v of the block as shown in figure 2.2. Okay. So air resistance is negligible. So from graph 2.2, meaning this is the initial speed. So initial speed U1 equal to 1.96 meter per second. Then after that go when the t equal to 0.2 second, velocity 0. So meaning at the maximum height, velocity equal to 0. Then after that velocity in opposite direction, meaning the block falls. Okay, block falls. V equal to negative 6.86 meter per second. So here all the time taken 0.9 seconds. Air resistance is negligible. A. State the feature of the graph in figure 2.2 that shows the block has a constant acceleration. So figure 2.2 graph velocity time graph. If you want to know the constant acceleration from the gradient. So from figure 2.2 we can see constant gradient. Okay. B. Use figure 2.2 determine the height of the block above the ground when the string breaks at t equal to 0 second. So here you have to calculate area under the graph. So this is the area 1 and then this is area 2. Okay. So for area 1, area under graph is a triangle. So half 0.2 times 1.96. So answer 0.196 meter. Area 2 half so from 0.9 to 0.2, 0.9 minus 0.2 times with the 6.86. So answer 2.4. So determine the height, change different in the area, 2.4 minus 0.196. So answer is 2.2 meter. To see the block has a weight of 0.86 Newton, calculate the difference in gravitational potential energy of the block between t equal to 0 and t equal to 0.9 second. Gravitational potential energy, mgh, so mass, weight 0.86 and height just now is 2.21 meter. So difference in gravitational potential energy 1.90 joule. Today, on figure 2.3, sketch a line to show the variation of the distance moved by the block with time t equal to 0 to t equal to 0.2 seconds. Numerical values of the distance are not required. Okay, now figure 2.3 given distance time graph but the time taken until 0.2. So we refer to the graph 2.2. What is the velocity? So when t equal to 0, velocity is 1.96 meter per second. Then when the t equal to 0.2 second, velocity is 0. This one showing that velocity is decreasing. Figure 2.3 given the graph distance time taken. So how to relate distance time taken with the velocity? So graph distance time taken, gradient. Okay, gradient of the distance time taken graph is velocity or speed. So we know that velocity is decreasing. So graph should look like this. Velocity decreasing. 2e, a block of the greater mass is released from the same height with the same upward velocity. Air resistance still negligible. State and explain the effect, if any, of the increased mass of the speed with which the block hits the ground. Okay. Air resistance still negligible, meaning acceleration no change because mass not affect the motion. This is the equation of linear motion. V squared equal to U squared plus 2AS. S equals to UT plus half AT squared. V equals to U plus AT and another one S equals to half U plus VT. So the equation of linear motion not affect with the mass. So mass nothing to do with the equation of linear motion. So acceleration not change. 3a, define force. Force is rate change of momentum. 3b, a ball falls vertically downward towards a horizontal floor and then rebounds along its original path as shown in figure 3.1. The ball reached the floor with the speed 3.8 meter per second. So initially u equal to 0. Then after that, the ball hit the ground with the speed 3.8 meter per second. The ball is then in contact with the floor at time t equal to 0.081 second. So time contact with the floor 0.081 second. Then after that, before leaving, speed is 1.7 meter per second. Then after that, rebound. So here, rebound, U2 is 1.7 meter per second. The mass of the ball is 0.062 kilogram. 1. Calculate the loss of kinetic energy of the ball during the collision. So kinetic energy must be kinetic energy final minus kinetic energy initial. So we have half m speed final squared minus speed initial squared. Half mass 0.062. Then we have 3.8 squared minus 1.7 squared. So answer 0.358 joule. B2, determine the magnitude of the change in momentum of the ball during the collision. So change in momentum must be momentum final minus momentum initial. MV final minus MV initial. Mass is 0.062, final negative 1.7 because in opposite direction, and initial was 3.8. So answer magnitude only 0.341 Newton second. (3b3) show that the magnitude of the average resultant force acting on the ball during the collision is 4.2 Newton. Resultant force. Force equals to rate change of momentum. So rate change of momentum is 0.341 and then time is 0.081 second. So 4.2 Newton. Yes, proof. Before, use the information in 3 to calculate the magnitude of 1, the average force of the floor on the ball during the collision. So average force of the floor equal with the average resultant force on the ball, the one that you calculated in B3, which is 4.2 plus weight. So we have 4.2 plus weight mg, 0.062 times 9.81, and answer is 4.81 Newton. The average force of the ball on the floor during the collision is same 4.81 because according to Newton's third law, force are equal but in the opposite direction. For A1, we define for a wire stress. So stress equal to force per unit area. Strain is extension per original length. B1, a school experiment is performed on a metal wire to determine the Young modulus of the metal. A force is applied to one end of the wire which is fixed at the other end. The variation of the force F with extension X of the wire is shown in figure 4.1. The maximum force applied to the wire is F1. The gradient of the graph line in figure 4.1 is G. The wire has initially length L and the cross-sectional area A. Determine an expression in terms of A, G and L, the Young modulus E of the metal. Okay, so Young modulus E equal to stress, strain. expressed is force per area, strain Lx divided by extension. So if we rearrange, we have FLAX. Because we plot graph, so we rearrange EAX LF. So we plot force is y-axis and then x extension is x-axis. So the whole thing is gradient. So gradient G equal to EA divided by L. So E equal to GLA. B2, a student repeat the experiment in B1 using the wire that has twice the diameter of the first wire. So here diameter equal to 2D, the original was 1. The initial length of the wire and the metal of the wire are unchanged. On figure 4.1, draw the graph line represent the new wire for the force increasing from F equal to 0 to F equal to F1. Area equal to pi d squared divided by 4. If area is twice, meaning 2, so we have area pi. So meaning area of the wire 2 is double from the area of wire 1. From the B1, E equal to GL divided by A, then EA GL. Then we know that the initial length of the wire and the metal of the wire are unchanged. So meaning length and the young modulus are constant. So A area proportional to the gradient of the graph. If the area increase double, so meaning the gradient increase by 4 times. So here is 16 boxes. So here draw 16, 4. So draw straight line. Okay. B3, another student repeats the original experiment in B1, increasing the force F1 to the new maximum force F2. The new graph obtained is shown in figure 4.2. 1. On figure 4.2, shade an area that represents the work done to extend the wire when the force is increased from F1 to F2. So work done is area under graph. So F2 area here, F1 here. So this is the work done, this area. Okay, this is the area. Okay, number 2. Explain how the student can check that the elastic limit of the wire has not exceeded when the force F2 was applied. So here, when force F is removed, wire can return to original length. Before each student in the class performed the experiment in B1, the teacher described the value of the young modulus calculated by the students as having high accuracy and low precision. Explain what is meant by low precision. So if we draw the target, so low precision showing that the value have a large range, something like this. So we can say that values have a large range. Number 5, a progressive wave Y passes a point P. The variation with time t of the displacement x of the wave at P is shown in figure 5.1. The wave has the wavelength 8 cm. Determine speed. This is graph displacement distance. Referring to 8, determine speed. Speed F frequency. So what is the frequency? Frequency is 1/time taken wavelength. So time taken from here until here, 0.4. So speed equal to 1 divided by 0.4 cm change to meter. So speed is 0.2 meter per second. B. A second wave Z has a wavelength 8 cm and amplitude 2 mm at point P. Wave Y and Z have the same speed. For the wave at point P, calculate ratio intensity of wave Z over the intensity of wave Y. So what's the relation? Intensity directly proportional amplitude squared. For wave Y, amplitude is 4 mm. Amplitude is 4 mm and wave Z amplitude is 2 mm. Wavelength same, 8 cm. So say that intensity equal to K squared. Intensity Z divided by intensity Y, Kx squared. So equal to 4 mm. Z is 2 squared divided by 4 squared. So ratio is 0.25. 6a, describe the conditions required for two waves to be able to form a stationary wave. So condition, the wave move in opposite direction and these two waves must be overlap and these two waves must be have same speed, same frequency and same wavelength. B1. Stationary wave on a string has nodes and antinodes. The distance between node and the antinode is 6 cm. 1. State what is meant by node. Node is 0 amplitude. Calculate wavelength. So from node to antinode is 6 cm. Node to antinode is quarter wavelength. So wavelength equals to 24 cm. B3. State phase difference between the particle at two adjacent antinodes of the stationary wave. So here if we draw, this is antinode, node and antinode. So two adjacent node and antinode and antinode. You have one node in the middle, so phase difference 180 degree. 7a, define ohm. Ohm is the unit of resistor. So B equals to IR. R equal to potential per current. So define ohm is volt per ampere. 7b, a uniform wire has a resistance 3.2 ohm. The wire has length 2.5 meter and is made from metal of resistivity 460 nano-ohm-meter. Calculate the cross-sectional area of the wire. So formula, resistor, resistivity, length divided by area. Resistance 3.2 ohm, resistivity 460 nanometer, length 2.5, calculate area. So area equal to 3.59 10 power negative 7 meter squared. 3.59 10 power negative 7 meter squared. C. A cell of the electromagnetic force EMF E, an internal resistance R, is connected to a variable resistor of resistance R as shown in figure 7.1. The current in the circuit is I. 1. State in the terms of energy why the potential difference across the variable resistor is less than the EMF of the cell. So, because we have here internal resistance, so we said that energy is dissipated in internal resistance R of uh, cell. C2. State an expression for E in the terms of I, R, and R. So by Kirchhoff's second law, sum of the EMF equal to sum of potential difference. EMF is E, IR plus IR. C3, the resistance R of the variable resistor is changed so that is equal to the R. Determine an expression in terms of only E and R for the power dissipated in the variable resistor. Power dissipated, formula power equal to I squared R. So power equal to I squared R because R changed to the R. So we want to know what is R. From the Kirchhoff's second law, E equals to IR plus IR. So R equal to R. So we have E equals to IR plus IR. E equals to 2IR. So current equal to E divided by 2R. So substitute here. Power equal to E to R squared R. So we have E squared 4R squared R. So we have E squared 4R. E squared 4R. Number 8 is state a similarity and difference between a down quartz and a down antiquartz. So similarity, same mass, or you can say same charge. Different, one is the down quartz and one is the down antiquartz. So opposite sign charge. Because one is positive, one is negative. B, for a nucleus of aluminium, 1, state the number of proton and number of neutron. So number of proton is 13. Number of neutron, 25 minus 13, 12. Show that the charge is 2.1 10 power negative 18 coulomb. So charge 13 plus charge 1.6 10 power negative 19 equal to 2.08 10 power negative 18 coulomb equal to 2.1 10 power negative 18 coulomb. 8C, the nucleus in B is moved along a straight line from point A to point B in the uniform horizontal electric field in the vacuum as shown in figure 8.1. The electric field strength is 11 kV per meter. Calculate the work done to move the charge from A to B. Okay, so move charge from A to B. What is the work done? So work done equal to force times distance. So first we have to calculate force. So given the electric field strength, force divided by charge, electric field strength is 11 kilo. Want to calculate force and then charge. Charge is 2.1 10 power negative 18. Force equal to 2.31 10 power negative 14 Newton. 2.31 10 power negative 14 Newton. Okay, distance. By definition of work done must be force times distance in the direction of force. So where is the direction of force? Electric field from the right to the left. So meaning the direction of force here also. This is the direction of force. So the distance is 4 cm. So answer 9.24 10 power negative 16 joule. Okay, so we done settle this paper. Thank you for watching. Bye.